All right, in this class, we are going to talk about sequential circuits. Click the week 5 tutorial. Let's do a quick review on it. It's been a while. I'm pretty sure you already forgot everything about it. So there are two types of sequential circuits: the milli sequential circuits and more sequential circuits. Okay, two different types. So how to differentiate these two types of sequential circuits? So the milli model, the output is determined by both the input and also the present state. If you look at this, sequential circuit, you can actually tell because X is the input and Q2, Q1, these are the present state. Y is the output. So the Y here is determined by both Q's and X as well. So this is a milli model, not a Moore model. Okay, if we have a circuit like this, how can we move forward to find out the logic equations and draw the state diagram and implement the circuit in Verilog? So that's the final goal. Okay. How do you convert the circuit into logic equations like this? So this will be something on the midterm exam in the future. So how to convert the circuit into the logic equation over here. I mean, if this is just a combinational logic, it's very simple since you can just use the signal lines and the operators to form the logic equations. But there's a flip-flop. How to deal with that? Whenever the clock rising edge arrives, it's going to send whatever at D to Q. Okay, so it's going to update the Q, the state of the Q here. So it used to be Qn, for example. So the next state of Q here, or Q2, becomes Q2n plus 1. Okay, and so first you have to find out the Q2n plus 1, which is the D here, because the next state is going to send this one to here. So that's why this becomes Q2n plus 1. And this is Q2n. That's a present state. That's a current state. Does that make sense? So now, for example, it's just a one state right now. It's before the rising edge comes. This is the current Q. This is the current Q2, Q1. And whenever the rising edge arrives, all these Q2, Q1, the present state, will be it's a combinational logic. So the whatever here used to be, it's going to already have a Q2 n plus 1 here. It's just waiting there. But whenever the rising edge arrives, it's going to send the data here to here. So it becomes Q2 n plus 1. So actually, the data line here is Q2n, for example. Here is Q1n. And I can use the signal line here and all the other ones as well to find out what is the signal here from the logic equation, which is this one. It's just combinational logic, very simple. And that signal is Q2n plus 1. And the same for Q1n plus 1 and Y. Any questions on this? No? Are good? So sequential circuit to logic equation, no problem. Okay. And then how to convert this one to the state table here. The three inputs are Q2N, Q1N, and X. And this is just a 3-bit binary number, and just keep incrementing by 1. So you can have all the 8 different types of inputs, and just plug into here, you can find out the output over here. So from the logic equation, you can find out the truth table or the state table of the circuit. Okay, so there's so task 1 is asking you to find out the sequential circuit from the logic equation. But however, it's already given here, so I'm asking you guys to not, just directly copy and paste these logic equations, but converting the state table into the logic equation and then to the sequential circuit. So how to do that? So I just gave you one example. So this is what I did. So this is for Q2N plus 1. So you are looking at this column, Q2N plus 1, this column. So you only look at the ones here, here, and here. So from the state table, you can find out the logic equation for Q2N plus 1, which is this one. All right, here. So if you have this logic equation available, you should be able to draw the sequential circuit out of it. How to do that? For example, we just forget about everything about this hand drawing. This is the only thing we know now. Can you draw the sequential circuit from this equation? How to do it? Yeah, combinational, but you need a D flip-flop. So for example, let me show you really quick. So if this is the only thing given, right, you'll design a sequential circuit from this. So Q2 so what I'm going to do is I will draw a D flip-flop first. So you definitely can use other types of flip-flops, but D flip-flop is the easiest one, right? Just draw the flip-flop first. Don't look at the equation yet. Just draw the flip-flop. Right? So you must be thinking like you need an inverter, but the D flip-flop can directly invert the signal for you. So you don't need to draw the inverter by yourself. So what's next? Have Q. These signal lines are the state N or state N plus 1. These are the state N's, not N plus 1's, right? So Q2 not, Q1, this is Q1, and X, which is the input, right? And AND logic, Q2, Q1 not, AND logic, and OR, and the output of the OR gate should be sent to the D, because that's the next state of Q2. That's how to do it. And so task 1 is asking you to do the same thing for Q1, N plus 1, and Y. Right, just follow this example, complete the task. The state diagrams. This is for the Mealy model. You can see right on the curve, on the arc, it has input / output. So that's a Mealy model. If you only have an input on the top of the arc, it's a Moore model. And in this tutorial, we don't have any examples for the Moore model. So all of them are for the Mealy model. It's very similar. So you can see that input output. So that's X and Y. That's a Mealy model. Okay. So section 3 shows you the implementation of the using Verilog for this sequential circuit. So I just directly put the logic equations over here. So for the module itself, it's very simple because for the main block of the module, you just directly use all these operators and signal lines to form all these output signals. However, there's one thing you need to be aware of. It is confusing of blocking and non-blocking assignment. Okay, and if I'm looking at these signals, the question here for you is, are these, so is Q2 here a new Q2 or old Q2? Old, right? So these are the final outputs, and these outputs are being assigned by these signal lines or the logic equations using what's the name of this assignment? Non-blocking. Okay. So they have to be registered, the reg tab over here. And I think I have a lot of explanation of this here in the first tutorial. If you scroll down to here, if these assignments are in the always block, right, and the sensitivity signal is the rising edge of the clock. So how many rising edges, how many clock cycles does it require to send X to Y2 here for this one? No, this is just one. It's going to happen immediately. Okay, and this one needs 3 clock cycles. And it can be confusing at the very beginning. So I have another a link to another website to explain all these concepts. Make sure to check it out. And come back to this tutorial. All right, so this is my code for the sequential circuit here. That's the same example as the one showing in section 1. So that's the module, that's the test bench. Okay. And here's the explanation of the simulation. And I didn't validate all these state transitions, but all the ones marked here, these are already validated by this test bench. And you don't have to use this exactly the same test bench as I used. You can change it a little bit, to test more transitions over here. So let's take a look at it, how that works. I just set up a counter over here, so the I starting from 0. If it's less than 20, then incrementing by 1. And every time I flip the clock, so I can form that rising edge, because in the module, it only detects the rising edge of the clock. Okay, so that's why I have to toggle it every time. And whenever I is larger than 5 and smaller than 10, I'm going to give x a 1. Otherwise, x is 0. Also, if I is 11, x is 0. If I is 12, I is 1. You definitely don't have to use the same numbers. But you can see what's happening here is the rising edge can actually detect the x here, the change of the x over here. So this is definitely not the best example, because how could you know that at the rising edge if it's updating x or not, right? Because it's transitioning here. So it's flipping from 0 to 1. However, so the rising edge of the clock can actually detect the 1 here, and at the same time update Q2 and Q1. Okay, let's take a look at it. So for example, so Q was 0, 0, Q2, Q1, so that's the that's a state. It's a 2-bit state variable. Originally, it was 0, 0. If x is 1, the next state becomes 0, 1. So it's going to change from 0, 0 to 0, 1, and y becomes 0. So let's take a look at it. So Q used to be 0, 0, and whenever the rising edge arrives, and also x is 1, it's going to change the state to 0, 1. So it's actually changing from 0, 0 to 0, 1. Okay, 0, 0 to 0, 1, and y equals to 0 as well, and y equals to 0. Okay, so now the state, so now the Q's, Q2, Q1, right now is 0, 1, it's in here. That's the current state, it's 0, 1. And here's the next rising edge. So x is 1, x is 1, 0, 1, x is 1. It's going to change the state to 1, 0, and y equals to 0. Let's see, 1, 0, 0. So the current state becomes 1, 0, and y is 0. Okay, you can verify all the other states. So now the state is what? 1, 0, right? Here, 1, 0, 1, 0. And next rising edge, x becomes 0. It's going to sample that x equals to 0. It's going to change the state to 1, 1. So 1, 0, x is 0. It's going to become 1, 1. 1, 1, and y equals to 0. Y equals to 0. And next, at the rising edge, x is 1. It's going to change the state to 0, 1. X is 1. It's going to change the state to 0, 1 here. And y equals to 1. Y equals to 1. So what about the... Okay, so that's a simulation by using this test bench. You can modify it a little bit if you like. But you don't have to. And using the behavioral model, behavioral form, here's a module, but same circuit, but a different way to model it. State is a variable, it's a 2-bit variable. So this method is going to be used very frequently in the near future. So the state is a 2-bit variable, and this is named as state A, B, C, D, like that, A, B, C, D, all right? If x is 0, and there's a case statement, if the current state is A, here, And if X is 0, it's gonna come back to the original state, to itself. Still A, right? So A will be assigned to state. So still A. If the current state is B, and if X is 0, it's going to come back to A. So assign A to state. Right? So on and so forth. Okay. And I provided most of the script, but I crossed out some of them to let you fill in the code in there. Timing in sequential circuits, shift registers. That's another important topic over here. Yeah, I want to explain some of the confusing part. So there are 4 types of shift registers: serial in, serial out, serial in, parallel out, parallel in, parallel out, and parallel in, serial out. And I think it's worth going all the concepts over here to help you understand this concept of shift registers. Okay, clock. So there are 4 types of shift registers: serial in, serial out, serial in, parallel out, parallel in, parallel out, parallel in, serial out. Okay. So for the first one, serial in, serial out, it's actually just a shifting to the right, and serial in, pumping in, and still one line, serial in, serial out. For the second one, serial in, parallel out, it's loading the data just in one line, and whenever the 4 bits are holding there ready, it's going to send all of them out at the same time. So it's a serial in, when the 4 bits are here, it's going to send all the 4 bits out at the same time. So serial in, that's serial in, parallel out. So what about parallel in, parallel out? It has all these input lines over here, so it's, and it has a D flip-flop over here to load it. Okay. So whenever the data is ready, load it to here and then send it out at the same time. This is the easiest one. Parallel in, serial out. So the data is being sent to here at the same time, parallel, and then being pumped out in a serial port, just one line. So these are the 4 different types of shift registers. And you guys are going to implement that in Verilog. For example, the first one, serial in, serial out, how that works. So each time it only updates. For looking at here, each time it only sends this one to here, but not this one to the final output, right? So it must be non-blocking assignment. Remember, if it's blocking, then it's going to immediately send to the output. It's just one wire. You know, if you want to implement all these registers in between, you must use this, okay? So that's a serial in, that's the original input being sent to Q3, Q3 to Q2. So it takes 4 clock cycles to send this data to Q0, to the LSB. All right, and you use a test bench to verify it. Here's a simulation. Let's repeat the work. And serial in, parallel out. So here is a little bit confusing. I want to explain this a little bit. So that's a serial, that's a input signal, serial in, it's just one line. And it combines with the other bits in the register and to form the final result. So serial in, parallel out, keep in mind, it's just one line as an input. It's being shifted to the right-hand side by each clock cycle. And whenever it reaches the 4 cycles, it's going to send everything out in parallel, right? So how that works. I mean, why this works for that purpose? Why this is the way to implement that idea? That's the new data, right? It's changing every time. And this used to be all zeros. So temp is a 4-bit data. It used to be all zeros. And now I got one new data. I put it here as a MSB. And I only take bit 1, 2, 3. That's 0, right? So I'm not using it. 1, 2, 3. So I'm going to use this one as a new 4-bit data and assign to temp. So next time I'm getting a new data input. So it becomes, I'm going to put it here. So it becomes this, right? And I assign this one to temp. Because I only take 1, 2, 3. I only take these 3 bits over here, right? Like this. And then combine with the new data. And next time I'm getting another new data because this is a serial in, it's always sending new data in just one line. So I'm getting another new data. Also put it at the MSB. So it becomes this, right? And I assign this one to temp. And eventually what I'm getting is all the 4-bit of the serial input signal, and I combine all of them into a 4-bit new data and send them out parallel at the same time. That's why this is going to do the work. Serial in, parallel out. It's going to do the work. So combining the new data with the old bit 1 to bit 3 data to form the new data, and eventually you are getting the parallel 4-bit data. So it's always assigning temp to PO, which is parallel out. That's the final output. Use a test bench to test it. From the circuit, run the simulation and verify it. Parallel in, serial out. Parallel in, serial out, how that works. See, it's always inserting a 0 to the MSB. Does that make sense? Parallel in, serial out. Parallel in, boom, you load it here. You load it here, and then you shift it out to get a serial out, right? When you are shifting it to the right-hand side, it's actually inserting a 0 in the front. Okay, how that works. However, yes, you are inserting the MSB, a 0 to the MSB. But you are losing the bit 0. So where's the bit 0? Serial out, right? So the bit 0 is actually the data being sent out, and you want to definitely keep it. How to keep it, though? Here. Bit 0 is being sent to serial out to the data output. Right? So the bit 0 is being sent out, right? It's already there, being sent to another signal line, which is the output. And bit 1 to bit 3 is being shifted to the right-hand side by 1 bit because I'm inserting a 0 to the MSB, forming a new 4-bit data. Parallel in, parallel out, super simple, just the 4 digit flip-flops. Right, just 4 bits, just do the assignment, very simple. The PI equals the PI assigned to PO, 4-bit assignment. Counter, and that's it. Okay, 5 tasks, 20 points for each. Due next Thursday. Any other questions? No?